Okay, welcome back from the coffee break. We have reached the point where we discussed absorption spectroscopy to be limited in use for turbulent flames, as well the method of laser-induced fluorescence to be problematic because of the effective lifetime. And that brought us back to this non-resonant technique based on Rayleigh and Raman scattering, where you shine in one laser, bringing up the molecule to something like a virtual state, and then observe scattered light, which is elastic Rayleigh, or inelastic, which is Raman scattering. And what we will do only is we will refer to the Stokes side of the spectrum for this concentration measurements. So that will be now discussed in some more detail. This method provides you the benefit that collisions, as in fluorescence measurements, are not of a problem at all. Because you have these scattering process, elastic as well inelastic, from all molecules in your probe volume, by only one laser excitation, you can measure multi-scalars instantaneously. Because the process is so weak, it's only those molecules that significantly contribute and are measurable that are called major species. And major species are species where in atmospheric flames the concentration is at least in the order of 1%. And so what will follow, main species will be measured by Raman, and Rayleigh will be used via the equation of state to determine the temperature. And that brings us to this view graph, where it is explained in some more detail why Raman spectroscopy at the Stokes site, here these two graphs, is useful for multi-species measurements. And this is exemplified here for two species, species 1 and species 2. The initial state from which the scattering process takes place, they're here at the same energetic level. Yeah, why not? We put them at the same level. And then we look for a Raman allowed transition. You bring up the molecule in a virtual state, it scatters back to that Raman allowed transition. Let's say this is a vibrational rotational state, and you have here for species 1 a certain energy separation. Yeah? Again, the vertical axis is the energy. And you do that same, you cannot prevent that, that happens as well in the same probe volume where you have the second species. This is characterized by a different energy gap between the two corresponding Raman allowed transitions. Yeah? This distance in energy is a different one than that. And that means that the scattered light is this upper arrow pointing down, given by the difference of the laser frequency minus this Raman resonance, this is this K1, this frequency, this energy, this wavelength of that scattered photon is a different one for these two different species. Okay? So you do have now a probe volume. You shine in your laser, and then from this probe volume you will have Raman scattering, it's not isotropically if you have a certain polarization, but let's leave that detail away for a moment. Then let's say you have here in this probe volume air, O2 and N2. That is the major species here. Then the scattered Raman light would have one frequency for O2 and another one for N2. And that means you just need a spectrometer, and then you disperse that. You just spatially separate these two frequencies, and then at the exit of the spectrometer you would have maybe here the O2 line and here the N2 line. And by that you have a possibility in one probe volume, upon excitation of one laser, to see, in that case of air, two Raman species that show up after spectral dispersion on your typically CCD detector. So I make a break. Is that understood? Because that's the basis of the technique.
You actually get multiple lines, don't you, for each one?
Yeah.
You actually get...
Exactly.
Okay.
The question was whether we get multiple lines. I've shown that only for one transition. Of course, you do have here, if this is the vibrational state 0 and this is the vibrational state 1, then you would have here multiple rotational lines. And let's say we take the Q branch, and then you would have as well here transition to multiple rotation lines. And of course, we do have then the superposition of different rotational, vibrational Raman transitions. That's more precisely here. That is a schematic for only one transition out of many. And depending on the molecule, that can be really many. CO2, for example, at 2000 Kelvin will have something like 100 million transitions that are superimposed to each other. It can be a huge number. Yeah? So no chance to spectrally disperse them. Okay, so in atmospheric flames, we have, as I said, because the process is rather weak, only access to the main species. And the main species meaning at least 1% or so, such that intermediates like OH, for example, are not detectable. So what we can measure, and the list is given here, CO2, oxygen, CO, nitrogen, methane as fuel, water vapor, and hydrogen. And based on these species, which sum up to nearly 100%, neglecting the intermediates, maybe it's more correct to say 99.5% for a stoichiometric methane air flame. As well, you can deduce the equivalence ratio or the mixture fraction, and from Rayleigh, as you will see, the temperature. Why is that not so often performed? The problem is the low Raman scattering cross-section in combination with high temperature atmospheric flames having low densities. So you just have in your probe volume, of course you want to make this probe volume very small to have a good spatial resolution, let's say 100 micrometer to resolve as well flame fronts. Then you just have a few Raman photons left over, even if you shoot in a lot of energy. And that is a problematic. Of course, in turbulent flames, you want to have that as single shot. So you always fight against noisy data, and that's why data evaluation really is very, very, very critical. And I will, for that reason, stress here or discuss that in some more detail. Nowadays, of course, we want to do that 1D. Why that? Of course, with high spatial resolution. We are interested very often in this context, really in the structures of flames. And that means you want to have derivatives. In non-premixed flames, scalar dissipation rate. In premixed flames, thermal dissipation rates. Yeah? And those gradients, where then you need at least along a line the information about these scalars. Here's an example, bringing back that more than one line is involved. I would like to remind you that we have selection rules given here for the J levels only. The selection rule for the V, for the vibration state is +1. The most intense you see is the Q branch, where you're changing the vibration state from 0 to 1. With the Q branch involved is no change in the rotation level. So the rotation level in the vibrational ground, an excited state, is the same. And this is calculated here for oxygen in a so-called stick spectrum, where you don't care about the line shape. You see that the Q branch here is much stronger than the O and the S. The P and the R are so tiny, forget them. They're not allowed here for oxygen, very, very small amount. Okay, so that is what you would calculate theoretically, but I have said, you disperse that in a spectrometer. And because you want to measure all these species, your spectrometer will cover a range of 150 nanometers or so. So your spectrometer does have a very bad transfer function in the sense of the line width. And so I will draw that here separately. If this is your wavelength, take the wavelength axis, and you would have here your single row vibrational transitions. Then your spectrometer makes out of this something like that, which is spectrally really broad. And you have many of these lines. And so all these different shapes are superimposing, such that in the end, in the spectrometer, you might see only something like an envelope. Yeah, this is roughly, yeah? You understand, you got the point. Yeah? You cannot separate these different rotational vibrational transitions. They're one mass, such that you end up to see only a band. And this is what you see here. So first of all, you need a laser which can operate with fixed frequency. You don't need to tune it to a certain resonance. That's good. No dye laser or so. But the bad thing is the process is weak. That's why you need a really lot of photons over here. Then you focus them without making a breakdown. Maybe I should discuss that a bit more. Then you image that onto your spectrometer, and then you use a CCD camera, low noise camera, to finally get a spectrum. And because we're interested in all these 7 main species, and use here 532 nanometers because of cost reasons, that are lasers working reliably and providing good pulse energies. Upon 532 nanometer excitation, you see here the spectrum spreading from 560 to 680 nanometers, containing CO2 and all the others down to hydrogen, such that the dispersion is rather coarse. And let's take, for example, the water vapor over here. There are many transitions involved, which you can't resolve, as I discussed before. To give you an idea, in our model for water, maybe 30,000 lines. We have seen that for the oxygen a second ago, possibly in the order of 2,000 lines are involved. And in CO2, this is up to 100 million lines involved. So only 3 atomic molecules, but extremely complex. Okay. And so what you get then after spectral dispersion is these nice Raman spectrum. And one possibility is to theoretically calculate a spectrum and then fit it to the measured one. But, and that needs more discussion, more attention about how to handle this data. The red one is the measured one, and you see a lot of noise in that. And that is because you spread your small signal over many pixels, and you don't bin them together. And that's why this is although it's a beautiful technique, it's critical in terms of noise. However, we have to look further into how this is evaluated, and ideally then in the end you get from Rayleigh the temperature and these 7 main species, which nearly sum up to 1 if you add up all mole fractions. Okay, the question is how to achieve this many photons that are needed to get a reasonable Raman signal. So ideally you take a laser that has something like, I don't know, 3 joule in the green. In principle you can build that. But if you would focus that within 5 nanoseconds, you would have just a spark. Yeah, that would be a very bad thing. So people came up with the following options. First of all, they use not a single laser, they use a burst laser. A burst laser typically consisting of 4 cavities. Already instead of having, let's say, 1 laser with 2.5 joule, they use 4 lasers, each with 600 millijoule. And then they can be combined with each other, but fired sequentially. But even if you have 600 millijoule and you focus that down to 100 microns or 150 microns, you will have a spark. So you need to keep the photons, the number of photons, the energy, but lower the intensity. And that is done by a delay line. Yeah? And a delay line works like that. You have here from your burst laser system the incoming beam. And then you have a beam splitter that reflects one part of the beam directly towards the experiment, but a remaining part which is transmitted that goes to a delay line. And the delay line is constructed of typically 2 mirrors, which are 100% reflective, as good as possible, such that you then feed the pulse that has been transmitted and directed to the delay line onto this beam splitter from the other side. And again, a part of that is then again reflected, another part is transmitted. And the beam splitter, a good choice to have a transmission of 60% and a reflection of 40%, such that if you now have here the time, the leading pulse, let's say the first pulse, and I assume here now a top hat profile, of course it's not, is here maybe 5 nanoseconds long. And then depending on the length of the delay line, that is something you have to choose. Here just remember that 1 nanoseconds corresponds to 3.3 meter, roughly. So if you have 5 nanoseconds, that means your pulse is 1.50 meters, And if you just want to use one delay line, for example, then take the delay line of 1.5 meter, and then the next pulse would come after that. And now you can easily calculate what the intensity would be, neglecting any losses in the delay line. If you have here 60/40, that would be here at the pulse intensity of 0.4. That is 0.6 times 0.6. This is 0.36, and then it decays further on. You can calculate that maybe on your own. And of course, infinitely long, but after a couple of round trips, it's down to 0. Okay, and this one delay line typically for half a joule pulse is not sufficient. People in the literature, you will find solutions with either 2 or 3 delay lines. And with that, you bring down the intensity, and it's only the intensity which is important to create a spark, but you keep the number of photons, you keep the energy. Of course, you have losses, but the losses are maybe 20%, such that you still have a reasonable pulse that comes now as a burst into your system. Yes, please.
You mentioned one of the slides that you would do this Raman spectroscopy as a 1D.
Yes.
So could you actually resolve the mole fraction concentration of methane through the flame front?
Yes. The question is 1D. You do that along a line, and I will show you the spectrometer, how to do that. That you have, let's say, with the separation at Sandia, it's roughly 100 micrometer they can achieve at best. Along a line, the mole fractions and the temperatures as well across the flame front. And that is what we're after. We want to understand how the flame structure is changed, for example, if you add hydrogen, or if you crank up your turbulence intensity, for example. Exactly. Then you get it along one line, but not 2D and not 3D, unfortunately. Spectrometer. Of course, you can spend a lot of money into the laser and add maybe laser 5 and 6 and so on, but it's even better and if you have a good spectrometer. If you take a commercial spectrometer based on Cherney-Turner type spectrometer, the transmission is frustrating low. It's maybe only 40% going through that device with the grading and these mirrors. And it's not good for imaging as well. And that's why it's better to use a transmission grading. And there is one company called Kaiser Optics, located in the US. They provide very high quality transmission gratings with 1200 lines per millimeter, more or less what we need for our dispersion. And then instead of having a spectrometer with reflection, where you have mirrors, you use instead of that high quality lenses, either from Canon, Nikon, Leica, whatever, and use them. And so what you see here is a design that you will find in Darmstadt, but as well in Sandia. You have here the Raman Rayleigh scattering that has been collected. Use a large lens. It must be achromatic. Yeah, there's one supplier providing that. And here you have the 1D line. Okay, you have here somewhere the Imaging optics, and here is your 1D line coming from that burst laser, let's say 150 microns diameter in both directions, and that is then imaged. How is that imaged? First of all, you have this periscope over here, 2 mirrors. By that you change the orientation from horizontal. Typically you go in horizontally, and then you have here this changed by 90 degrees, and you have a first slit over here, where the focus of this imaging lens is at this slit over here. And because later on we use CCD cameras, this is a stationary slit, and you have a wheel as well with the slit, which is rotating. And thereby you have a mechanical shutter. Okay? You do not like to have any intensifier here. Intensifiers is so noisy, and that's something we cannot afford to make quantitative measurements. That's why if the flame is luminous, you have to somehow limit the exposure, because these CCD cameras, backside illuminated, low noise CCD cameras, they have a shutter inside, but it's by far too slow. That's why this is a rotating wheel. After that, you have a lens system that again parallelizes the beam, which contains Raman and Rayleigh, all these different colors. I go back, all these different colors plus Rayleigh, which is not shown, is still contained over here. Then this is a beam splitter, and that is the Rayleigh is going to that camera. This is 532 nanometers from the Rayleigh scattering, is then imaged over here, and this would be a vertical stripe denoting the density, of course, dependent on the gas composition. And then the remaining Raman is going this direction and is then focused here in the spectrometer. The spectrometer is this part where you have again a slit, and because Raman is even more prone to backlight, you need a shorter exposure. That's why you have again here a constant slit and a rotating wheel, but this wheel is even faster than the other one, such that the exposure time in this system has been reduced to something like 4 microseconds. A mechanical shutter with 4 microseconds, that's extremely short. Yeah, if you take an iris, that's in the millisecond regime. Yeah.
And you read it out, you have it, do you have it phase locked?
Yeah, yeah,
Okay.
yeah. So that is the stationary slit, and then the rotating wheel with the slit comes, and when they match, transmission, and mismatch, no transmission. And now you have to control the rotation of these wheels. They have to be simultaneously, they are driven by own motors, and they have to be synchronized with the laser. And so in the old design, these rotating wheels have been the master, but that's not so good. Nowadays, the laser is the master, and we have built a control unit that allows us to synchronize that very precisely.
Phase locked.
It's phase locked, exactly. And then you have here the grading, 1200 lines per millimeter, such that the different colors from the different species are dispersed, and the low noise camera then looks at these different bands. And here you see that instrument that has been developed then with different master theses supervised by a PhD in my group, with many optics. In the end, of course, it's not cheap. Yeah. But it's, I think, a nice piece of optics, and it took actually 2 years to come then up with a solution that seems to work.
These are all very good anti-reflective optics.
Oh yes, oh yes, yeah. They're not the cheapest ones. Then about the post-processing. Now we come closer to what to do with the data. So first of all, I have to point out the fact that the Raman signal of species I at a certain location is proportional, of course, to the parameter of interest, to the number density of that specific species at that location. It depends on the laser energy that is sent in, and it depends over the polarizability on the Raman cross-section. Different species have different cross-sections, so they can differ enormously by a factor of 10 between hydrocarbon and nitrogen, for example, because those electrons are more or less strongly bonded to the nuclei. The problem comes with the fact that these cross-sections are temperature dependent. And this is a strong dependency. And so without knowing the temperature, you're lost. That's why in that setup, Rayleigh scattering is simultaneously used to determine the temperature. And the Rayleigh signal at a certain location depends on the number density, and thereby the density of all molecules inside the probe volume, on the laser energy, but as well on the cross-section of Rayleigh. And we have discussed that already. This is dependent on the mole fractions of each species in that probe volume. Once you have that, you can use the ideal gas law and deduce these temperature. And so what the idea now is that you determine the gas composition and the temperature iteratively. And you start with a good guess. And a good guess is, let's say, take 1000 Kelvin. Take 1000 Kelvin, put it in here, then you know the Raman cross-sections, you measure that signal, you measure the laser intensity, and with a method that needs to be discussed, in principle you can determine now the different species concentrations. Once you have that, you use that information, you put it into your Rayleigh signal, where you have measured the Rayleigh intensity. Now you have a first estimate of the Rayleigh cross-section. You have measured the laser intensity, and then you have a first estimate of your number density. And then with the ideal gas law, you update the temperature, and you follow that cycle until convergence. And convergence can be defined, for example, that the temperature does not change more than 1 Kelvin. And then this is done after 3 or 4 iterations. That's the idea. Now, the only thing that is left is how do we do this upper part? How do we really perform the post-processing in terms of Raman? I think the lower one that is more clear. And so there are two methods which are very different that have been developed. One that has been developed in my university, it's called spectral fit, where you disperse the spectrum with this spectrometer, and you calculate a theoretical spectrum, and together with a background, which is shown as this purple line, you try to fit your model to that noisy data. That is a nice and beautiful thing, very similar to cars, but you have noisy data, because after dispersing them, weak signal, it's not as good as you sometimes wish. The other method has been developed at the Sandia National Labs, and it's called the matrix inversion method. The basic idea is the following. You do have here a vector of signals, the signal from CO2, from O2, and so on, the whole row. You have as well connected to that the number densities of these different molecules. And they are interconnected here by a matrix. And this matrix contains all the temperature dependency. Once you have determined that matrix and you measured that signal, you just make an inversion of that equation, and which is shown here, and by that determine the number density. That is a technique where I go into this upper graph. It's done differently. Here, you do an on-chip binning. You have in these areas where the Darmstadt method has dispersed the information to get this band. In the matrix inversion method, you don't care about that. You just take all the information and you just integrate that information from a certain range. And thereby you have just one scalar value, for example, for water, where in the spectral dispersion maybe you have here 50 values, but noisy. Yeah? Spectral information with high noise against no spectral dispersion in this area because you have binned that up, one scalar value which is less noisy. And so what I would like to show is we have, in a collaboration with the Sandia National Labs, combined that to the hybrid matrix inversion method, because the problem coming along with this method here, as you will see in a second, that needs a heavy calibration. And this heavy calibration is as well something which makes it impossible to be used with this transmission grading spectrometer. And that's why we try to combine the strengths of both approaches. And because, just a second to finish that sentence, because that has been presented by that time 7 years back in Beijing by Rob Barlow, I left these transparencies as they have been used for that to make sure that is a presentation that was given by Rob Barlow, and that's why you find these Sandia National Labs transparencies. The other authors are all from Darmstadt. Your question, please.
Two questions. So if, let's say I wanted to measure the species concentration through flames, like how much upfront effort is it to set the system up? And
Okay.
the second question would be, would it be possible to extend this to a planar measurement using something like hyperspectral imaging?
First question, what is the effort? The effort is large. The principle is known and very simple and a charming idea. The problem is you have really to achieve very, very low noise. And that means you need the best components on the laser side, on the detection side. And so you need a lot of investments. I cannot directly say how much. You need as well a long-lasting program to come to that point. I've seen groups trying that and stopping that because they failed. And if I refer back to the last 20 years, it is maybe the most expensive experiments with the less publications. And you need as well people doing that in the lab with a high level of frustration. Okay, the second question, to do that 2D, then you cannot use it in the way shown here with this spectral dispersion in the spectrometer, because there you just have a slit and thereby a line, which can be then, this line corresponds then to the different locations in your 1D probe volume, which are then dispersed. So you cannot expand that in that way to do the 2D thing. You mentioned hyperspectral. I have to think about that, whether this is possible. I haven't. But you must somehow achieve then. So with a simple spectrometer, no, it will not work.
And a follow-up question on the first one. Is it possible to move these setups, or is that also does it become a huge effort because you put so much work into lowering the noise?
You can't easily move that. Wolfgang Meyer from the DLR in Stuttgart, he has built up a transportable Raman system, and he has brought that. I think he was, the only transporting that, but they had as well funds to do that to locations somewhere else where they measured in high pressure combustion. And they have done that. In the Sandia system, you will see that in a second, similar to the Darmstadt system, they're immobile.
So it's not like a PIV system
No.
where you can do business?
No. It's not. It takes, in principle, you can make it movable, but then you need extra money to make that, and maybe some extra time and very experienced people to build that up in the new location. So I think we can skip the part over here. It's clear you want to have these major species and gradients, scale dissipation, we mentioned that, 1D. You want to have a good accuracy and precision, and that is given here because you do not have any problems with this collisional quenching. And we will see here these two methods that are combined to the so-called hybrid methods combining these strengths. And then I'll show you some application here. So first of all, the matrix inversion that has been developed in the Sandia National Labs, where you do see here, again, this matrix. S is the signal vector. Then you do have this matrix with these different matrix elements. All of them are temperature dependent. And then you have the species vector. That is now given here from CO2 down to H2. He included as well CO live. He included as well here a channel looking for C2 fluorescence and a background. And then you see correspondingly to that here the species vector and interconnected by this matrix. And now comes the problem. In an ideal world, if everything would be separated spectrally, you would have only here matrix elements at the diagonal. But you see here as well off-diagonal elements. And I go back to this view graph over here. The problem is, let's take an example, CO2 and O2. They spectrally overlap. We call that a crosstalk or an interference. So if you have here a certain limit where you integrate all your CO2 information, there shoots in O2 information, and the vice versa. The same holds true for N2 and CO and so on. And that's why you find here at those locations where you have these crosstalks as well matrix elements. Yeah? So which means that the CO2 signal is composed of this product that is of what you're after, but because of the crosstalk as well, the O2 shoots in and so on. And all where you find dots, these are the crosstalks that needs to be considered. You got the idea? Once you have these elements, you can do the inversion and calculate it. But in former times, this has been done on calibrations. All these matrix elements have been obtained from heated gases and a huge variety of different calibration flames to get from 300 Kelvin to 2000 Kelvin. And that takes time. And that has been done in the times where it was not yet 1D. There it was done and was okay. We come to a point why you cannot apply it with a transmission grading in a second. Yes, please, the question.
So the matrix is for a particular temperature?
No. The matrix contains elements which are polynomials where the temperature is a parameter. Or the question is, I have to repeat that, sorry. This is not the question was, is this a matrix for one temperature? It is done in that way that each matrix element is a polynomial dependent on temperature. Okay? For a given temperature, then you have one realization. Go to another temperature, then you have another realization. In that sense, you're right.
Presumably, this is an overdeterminate matrix with many more lines than you have species.
Yes, it's over. Yeah, exactly. Let's have a look at the TU Darmstadt approach. There, as I said, everything is calculated or simulated as good as possible. This is summarized in this Ramses code. Then each of these transitions, I said up to 100 million at CO2, is convolved with this transfer function of the spectrometer, which needs to be measured. And then you get a library, and then you can do and try this spectral fit. It has been a major part of one thesis 15 years ago. The pros and cons: matrix inversion, where you bin everything from one band to one scalar value, provides lower noise, and that's the real benefit. It's much faster. But if you do it in the old version, it needs these huge calibration efforts, and at some conditions it's difficult to find something. For example, how do you want to calibrate for water vapor at 300 Kelvin? Difficult. I don't know how to do it. Spectral information is lost. That can be a drawback if you have, let's say, competing species, for example, C2 live or background that shoots up. You don't recognize that. And it becomes impractical if you have beam steering or using a transmission grating. And that reason transmission grating comes in a second. Spectral fitting, based on quantum mechanics theory, is in that sense good because it's based on a physical sound model. You need to calibrate only for each species at one point. You have to shift simply depending on your collection angle, detection efficiency, and so on. Beam steering is handled automatically. Background can be corrected, but the readout noise is high. That's bad. It takes time. And so much expert knowledge, such that people in my lab have taken the data, and then a year later they came out with the results. Forget it. It's not good. So because typically then you have to go back and redo the experiment, and that's not good. And so really a significant effort. Now we come to that question whether the system is mobile or not. This is the Sandia version, having here the set of lasers which are fired sequentially, 3 delay lines, where I have shown how one is constructed. This burst is sent through the region of interest. You have the 1D line. We forget these sheets here that are to look for the orientation, how the line is intersecting the flame front, because that's of course important. Yeah, you will have a flame structure, different, identical flame like this or like this. Yeah, that's why that is done or combined here with crossed sheets. And then you get a 6 millimeter segment with 100 microns resolution along the line, and the diameter is something like 1/e square in the order of 150 microns or so. And then you can as well, in principle, get these gradients. So they have a very similar setup here with this spectrometer, with a Rayleigh camera, additionally a CO lift camera, then this grating here in the Raman camera, and here you see a ZMAX model of that. With a rather good as well line spread function in the order of 50 microns. And the key of that is this transmission grating from Kaiser. And you see here as well the 4 microsecond gauge time. Very short exposure. Now we come to the problem with the transmission grating. You see here the nitrogen taken in air. This is the spatial dimension. This is along the slit. This is along the 6 millimeters. And this is the pixel, meaning the wavelength direction. And an ideal spectrometer would give you a line which is here in terms of wavelengths just straight. But for reasons to be read in this article, these transmission gratings make a so-called bowing. They have spectral dispersion which is different at different spatial locations. And if you now subdivide these 6 millimeters, let's say in 60 probe volumes, each spanning for 0.1 millimeter, then you would have to do for each of these, Barlow called that stripes, for each of that stripes you would have to do a calibration. That kills you. So using that nice spectrometer needed to somehow do the calibration combined with our theoretical approach. And so first of all, a few more information about the spectrometer. You see here the dispersion. Dispersion is nanometers per millimeters. You find that it's not uniform. That must be accounted for. You see here the spectrum of a neon lamp at low pressure with known transitions, with no wavelengths. Thereby you can make simply this dispersion, not only rely on ZMAX calculations, but as well measure that. And this lamp has been positioned behind a plate, and this plate had a number of holes. And there you now nicely see the bowing. If I follow something like this line here, that is slightly curved. It's not much, but it becomes clear why this is a problem in a second if you do the matrix inversion. And this is here. You see here, for the example of nitrogen and water vapor at low temperatures and flame temperatures, the spectrum. That is measured red, and with this transfer function of the spectrometer as well simulated. And these dashed lines, these are the lines which are used for integration, for binning in the matrix inversion. If you have a low temperature, the nitrogen line is completely contained. But if you now go to higher temperatures, more clearly here for the water vapor, you see that because of more rotation lines to be populated by Boltzmann, the band is getting broader and starts to leak out. And that means that these binning regions, which are due to technical reasons in the CCD camera fixed for the whole chip at 1 pixel row, such that the spectrum, if you have the bowing, you can imagine that this outflooding of that spectrum is different for each spatial location. And that needs to be accounted for. If you do that now theoretically and calculate all these matrix elements based on theory, you can pre-calculate that for each stripe. And that is the charm of the system here. And that brings us to this chart. So based on this calculation and comparison, we see the calculated spectra behave well. They are like the measured ones. Unfortunately, only for 6 species. We can't do it for methane. And then you see here each species, CO2 down to hydrogen. You see the different temperatures. And then you see here color-coded the intensities. And due to Boltzmann distribution getting broader, you find for higher temperatures the spectrum of CO2, O2, and so on is getting wider. And you see again here these dashed lines. Those are the integration borders in which all the information in the hybrid matrix inversion method is binned together, is summed up. And you see as well now, taking CO2 as an example, that we do have crosstalk from O2 at higher temperatures getting worse, as well as from hydrogen. So these are these crosstalks that have to be accounted for. So we can calculate that now. So the solid lines of the CO2 response, these are now these polynomials in these matrix inversion. Black are measured, the green symbols are calculated, and then you see as well a calculation if you shift your integration by plus minus 5 pixels. That could be due to beam steering, but you see now as well the sensitivity that happens due to the bowing from the transmission grating. That makes a huge difference. Depending on the molecule, more or less, by CO2, it's significant. Here you see from O2 as well, the model is not perfect here, but as well a huge influence, and as well for other species. And with this concept now, you can, for each stripe, according to this bowing effect, where you have locally a different dispersion, you account for that very nicely for the diagonal elements. And here you see again the crosstalk in an animation. Here I have magnified the CO2 channel. Here that's the O2 channel. And this is now, if you refer to the O2 channel, the CO2 lags in. So this is the crosstalk of CO2 upon the O2, or given over here, the crosstalk from CO2 upon O2. That can be as well calculated, measured black line, calculated green line, not perfect, but reasonable. Or the same here, the crosstalk of O2 upon the CO2 channel, such that you can say with these crosstalks, the uncertainty is a bit larger. It's not as good as for the diagonal elements, but with this, you can easily correct now for the bowing. It's a long story, isn't it? A lot of things that must be accounted for before you come to that point. Your question, please.
On the previous slide, the sum of the deviations, they were on the order of %.
Yes.
More or less. So does this actually become significant?
No.
Due to the error propagation?
Well, in those, it is not so important. The question is, again, does it matter when you have a % change only? For the water response, that behaves well. It's not so important. But for the others, that is significant. Yeah, for CO2, for example. And the error propagation is not so easy because you have this iterative loop. And so currently we try to optimize that automatically by as well adjusting these polynomials because of these effects that maybe your model is not perfect. Yeah, so you always tweak it a bit, and to optimize that is currently a project. Yeah, but it matters, and it depends for water less than for others. Okay, so I should finish that now. If you, for example, take here this flat calibration flame, operated fuel rich with methane air, where you should have in the exhaust somewhere here, there should be no O2 in the exhaust gases. If you do not correct for this Boeing effect, you see a change up to 2% error. That's not acceptable. We are already in these atmospheric flames that we reached a status that we must be much more accurate. If you correct now for the Boeing, that seems to be close to what you expect. Yeah? So we avoid this error. Of course, you can question, is it really important, 2%? Yeah, it is. If you're really at that level, we're assessing and modeling here, it makes a difference. If you now compare the old matrix inversion, the new hybrid method, the spectral fit, then you find for the mean species here in the case of a laminar hydrogen jet, where in the center you have laminar flow of hydrogen surrounded by a co-flow of air, then you find in the mean values some differences for those species which are at low concentration like O2. You find here that especially when you would do the matrix inversion with software binning, not hardware binning, that the noise shoots up. But it is more at the RMS where you see the differences. So the mean seems to be captured rather well by all methods. But if you refer to the noise, it is clear that this hybrid method in all cases is the best. And this is combined with the lowest effort in post-processing, and that's why that is used now in Sandia and in Darmstadt. So with that, I think it was a big step forward and makes it now easier to process these data, which is concluded over here. The key I just want to point out is that you have here the advantage of low noise because of on-chip binning. That is the key. You have a fast data acquisition and processing, and the processing becomes faster as well because you rely on the theory lying behind. Okay, and you can easily correct for this Boeing effects. With that, I think we are ready for an application example. I will make that a bit shorter than I thought, but we make that after the break, okay? So I would like to restart at 11:10.